Swayam Prabha. Digital India. Educated India.
A strategy Xi in player I strategy set is said to be strictly dominated for player I if there exists a strategy Xi dash in Si such that so this I am writing in the language of players minimizing. So, this is Xi dash comma x minus I is strictly less than Ui of Xi comma x minus I, and this has to be true for all x minus I in the set S minus I. What is the set S minus I? S minus I is simply the product over J of set Sj, J which is not equal to I. Okay. So, a strategy Xi is said to be strictly dominated for player I if there is another strategy that is better for this player regardless of what the other players play. Xi dash is always better than Xi and strictly so. Okay. Now, if the inequality above is weak, okay, that means it holds for this holds with equality for at least one x minus I, then we say that then Xi is said to be weakly dominated. Okay. So, that means if this inequality here is not strict for all x minus I, that means that it is going to be at least one case where the other players play some profile of strategies x minus I in which player I is indifferent between playing Xi and Xi dash. Okay, there is some case where these are the payoffs are going to be the same. In that case, we say it is weakly dominated. So then you have a less than equal to here rather than a strict less than. Right. Now, when you have a strictly dominated strategy, then rationality directly tells you that that player will not play the strictly dominated one. The weakly dominated is trickier because weakly dominated just means that there is still going to be a possibility that he will play one of these two in some case. Okay, so it's much trickier to say anything about weakly dominated strategy. But if you have strict dominance like this, then rationality directly tells you that player I himself will not play that. Okay. Now, how to make use of this, we will come to that in a moment. So, in fact, when you are this elimination of dominated strategies, right? If this has this property that I was just defining this, but essentially now what you can show is the following. Okay. Now, if you assume that, then you can eliminate strictly dominated strategies recursively one after the other. Okay, so long as they are available to be eliminated, you can eliminate, and it does not matter what order in which you eliminate. Regardless of the order in which you eliminate, you will actually end up with the same outcome. And finally, if you end up with a unique strategy profile at the end of it all, it turns out that that profile has to be the Nash equilibrium. Okay. So, if you can eliminate strictly dominated, if you find strictly dominated strategies in such a way that you keep eliminating and finally you are left with just one strategy profile, like it was in this case, right? If you go out here, I can now eliminate with one more level of assumption, I can eliminate also L for player 2, and then I am left with just 6, 2. You can check that 6, 2 is in fact a Nash equilibrium, and in fact the only Nash equilibrium. Oh, sorry, my mistake. Sorry, 4, 3. U, L is the Nash. Sorry, my mistake. Yeah, 4, 3. You can eliminate R. So for the sake of recording, I'll repeat this. So yeah, so in this case, for if you can do one more level of assumption and eliminate the strategy R for player 2, and then what you are left with is then just the strategy L for player 2 and a payoff of 4, 3. And you can show that 4, 3 is in fact the Nash equilibrium, and in fact the only Nash equilibrium of this game. Okay. So this was our definition of a strictly dominated strategy. Alongside this, I also need a definition for this assumption that we made. Okay. Now the assumption that we made was that, if you remember here, we assumed that each player knows that each player is rational, and then we assumed that each player knows that each player knows that each player is rational. Okay. And you can continue this recursion further and further, and actually go ad infinitum on this. Okay. So, and this is not just about rationality, we can assume this, we can make this assumption, we can talk of this kind of a recursive assumption, knowledge about any particular fact associated with the game, alright. So, that's what I will define right now. So, a fact or an event is said to be common knowledge among layers P1 to Pn if for any finite chain I1 till Ik. Okay, these are indices for players from, these are from my player set. The following holds. Player I1 knows that player I2 knows that ... player Ik knows the event. Okay. Now, this is the definition of an event to be common knowledge. So, an event is said to be common knowledge if for every sequence of that you can take, you can construct this sequence of players I1 to Ik. You can repeat players also along that sequence. The sequence can be of any length, right? And the following must be true, that player I1 knows that player I2 knows that player player Ik knows that event. Okay. Now, what does it mean to know is itself something I have not defined. So, that again needs a model. We'll come to that maybe in the next lecture or something. But essentially, this is what it means for something to be common knowledge. So, when something is common knowledge, it is not only that each player knows about that particular event, but it is that also the other players have witnessed him knowing it. Okay. So, the way events end up being common knowledge is when there is say a public announcement. Okay. If there is like a traffic signal, for example. Traffic signal, everyone watches the traffic signal and everyone else also knows that everyone else is watching. So, whatever is the content of that signal, it is known to everybody, and not only individually known to everyone, everyone knows that everyone knows, and everyone knows that everyone knows that everyone knows, and so on. Okay. So, events basically become common knowledge when there is a public witness of those events. Okay. So things that appear in the newspaper, public announcements, etc., those become common knowledge. Personalized notifications on your mobile phone are not common knowledge. Okay, things that come to you alone, the same thing may have come to others. Okay, but it is not common knowledge because they are just knowledge of individuals, but not common knowledge. Is this clear? Okay. So, this is actually an important distinction. It leads to one of these many of these sort of logical puzzles that you may have heard of about muddy children puzzles and so on. You can read up about this on the internet about the fine distinction between each player knowing a thing versus that thing being common knowledge, right? So, and that often the term used for this is that when each player knows a certain thing, we say that it is mutual knowledge, where each player knows that thing, but it is not common knowledge until all of these conditions actually hold. Okay. All right. Okay. So now what can be, so now since we are talking of games of that could have basically an arbitrary size, any number of strategies. If you want to start using the properties of dominance and to eliminate strategies, effectively what we need to assume is that rationality is not only that players are rational, but actually that rationality itself is common knowledge. Okay. When I told you also that when the prisoners were told this particular thing, they were each told this thing by the judge. Effectively, that matrix was also common knowledge amongst them. Each player knew this matrix, the other knew that he knows this matrix, etc., etc., etc. Okay. So, the standard assumption that we make in games is that payoffs, strategy sets are all common knowledge. So, those things are common knowledge. Rationality, whether we assume it to be common knowledge or not, really depends on the situation at hand. It is not a universal assumption that we always make in games. All right. Now, however, if rationality is assumed to be common knowledge, then you can use the properties of dominance in some cases to try and solve for the game. Okay, that's what we just used. So, I will now let me just state that in the form of an actual theorem. Okay. So, here's the theorem. So, let G be a game comprised of the following. So, you have n players, you have a set of strategies Si for the players, you also have payoffs Ui for these players. Okay. And now, suppose let G hat be this game which is formed from the same set of players, but a different strategy set, and I will tell you how these are related. S hat I for the players and the same payoff functions Ui. Okay. Now, S hat I is like this. So, S hat I is just the relation between S hat I and Si is that S hat I is a subset of Si, and this is true for all I. Then, so essentially G hat now is a game that is formed from fewer strategies, okay, than the original one. Some strategies have been removed or eliminated. Okay. Then, if X star equal to X star 1 till X star n is a Nash equilibrium of the original game G, such that X star I belongs to S hat I for all I, then X star is a Nash equilibrium also of G hat. Okay. So, what is this theorem basically saying? So, suppose let G be a game, and then you construct another game G hat by eliminating some strategies from G, right. So, the elimination is captured here. S hat I is a subset of Si, And now suppose X star is a Nash equilibrium of G. Okay, if X star is a Nash equilibrium of G, such, and with the property, with this property, this is important, with the property that X star I is in S hat I. So X star is actually feasible for the game that you have formed after elimination. Okay, then X star is also a Nash equilibrium of G hat. So you have your original game, you have a Nash equilibrium of that game, you have another game that is formed from eliminating some strategies, but after elimination this Nash equilibrium is still present in the smaller game, right? Then the claim is that that is also a Nash equilibrium of the smaller game. Okay, and the proof is very simple. So let's just quickly do the proof. So we clearly have, so X star is a Nash equilibrium. So U of X star, Ui of X star I comma X star minus I is less than equal to Ui of Xi comma X star minus I for all Xi and for all I in N. Okay. Now, since this is true for all Xi in Si, this is naturally also true for all Xi in S hat I, because S hat I is a subset of Si. Okay, so therefore this we have that this is X star I comma X star minus I is less than equal to Ui of Xi comma X star minus I for all this and also for all I in N. Okay. Now only thing left to argue is that these X star i's are actually in S hat I, and that is given to us by assumption. We have been given this right here, that X star I is in S hat I. Right. So in other words, the point X star satisfies the conditions of a Nash equilibrium for the game G hat. Okay. So which means X star is a Nash equilibrium of G hat. So this is all I have used here is that, see, basically player in X star being a Nash equilibrium of the bigger game G, he has no incentive to deviate to any other strategy in G. And since S hat is a smaller set, is a subset of the strategies in G, so therefore he has no incentive to deviate to any other strategy in G hat also. Okay, and only thing for me to guarantee that is left for me is that for me to prove is that X star actually is available in G. It's not gotten eliminated out when you created G hat. So X star is actually available in G hat, and it has not been eliminated out. All right. So this is one property. So what are we learning here? We are saying that if you eliminate strategies, and if the original equilibrium is available in the smaller game, then it is also an equilibrium of the smaller game. Okay, almost obvious sort of statement. Okay, so now let us now talk about elimination of weakly dominated and strictly dominated strategies. Now suppose G hat, let G hat be obtained from G by elimination of a weakly dominated strategy. Now here is a statement you can say roughly in the opposite direction. So G hat is now obtained from G by eliminating a weakly dominated strategy X hat J of a player J. Okay, so there is a player J who has a weakly dominated strategy X hat J. and that strategy has been eliminated, and the resulting game is called G hat. Okay. Now, the claim is this, then every Nash equilibrium of G hat is also a Nash equilibrium of G. Okay. Now, what does this mean? The previous theorem, what did it tell you? If you eliminated some strategies and the original Nash equilibrium is still available after elimination, then it is a Nash equilibrium of the new one. Okay. This theorem, what it is saying is that every Nash equilibrium of the smaller set, of the smaller game, is necessarily a Nash equilibrium of the original game, which means that elimination of strategies cannot create new Nash equilibrium. It can at the most eliminate Nash equilibria, but cannot create new Nash equilibria. Okay, all right. So, what is S hat now? Now, S hat has the following structure. S hat, for this player J, it has particular player J, it's obtained from eliminating some weakly dominated strategy, whereas for others it is the same as before. So, this is equal to, so S hat I is equal to Si for I not equal to j, and it is equal to Si minus this Sj minus this specific strategy x hat j for I equal to j. So, for I equal to j, you have removed the strategy x hat j. Okay. So, for all other players I, S hat I is equal to Si, and for player j, it is equal to Sj minus this weakly dominated strategy that has been removed. Okay. All right. So, now let x star be a Nash equilibrium of G hat. So, which means what? That means Ui of xi star comma x minus I star is less than equal to Ui of xi comma x minus I star for all xi in Si and for all S hat I and for all I in. Okay. Now, this note, this is for all I in xi in S hat I, but S hat I is equal to Si for I not equal to j. So, that means for I not equal to j, I can write this as basically this condition forks into two cases. So, I not equal to j, this is actually the same as saying xi in Si, and for I equal to j, this is all Si except for all Sj except for x hat j. Okay. All right. Now, what do we know about? So, essentially, now if I want to show that x star is a Nash equilibrium of, I have started assuming that x star is a Nash equilibrium of G hat. I want to show that it is a Nash equilibrium of G, which means that I would have to show this for this inequality for all I. For all players I and for all xi in Si. Now, for I not equal to j, S hat I is equal to Si. So, there is no issue here. Okay. This takes care of players not, all players I not equal to j. But for player j, I can only take care of it partially, because I can take care of it except for this strategy x hat j. So, I do not know if strategy x hat j could be better than basically x star j here, right. So, but then let us see what x hat j actually was, right. So, if you see what was x hat j was weakly dominated. Okay, which means what? If it is, since it is weakly dominated, it means that there is at least one other strategy which is better than this one, right. It means there exists, and it is weakly dominated where? It was weakly dominated in G, right. G hat has been obtained after removing x hat j. So, it was weakly dominated in G. So, that means there exists a strategy, let us call it say Tj in Sj, okay, such that playing Tj is better than playing x hat j, regardless of what the other guys play. Is this clear? So, regardless of what the others play, it's better for player j to play Tj as opposed to x hat j. Okay, and I have a weak inequality here because this is weakly dominated. Okay, so I have a great this is sorry, if I written a greater, my mistake. It should be less than equal to. Yeah. So this is less than equal to, yeah. So Tj is better than playing x hat j, regardless of what the others play. Okay. Now what do I do? Well, this is true for all x minus j, right, regardless of what the others play. So I can actually make the others play their starred strategies from here. Okay. So let's pick these starred strategies. These starred strategies are in G hat, remember. So they have not been eliminated. They are actually present in G also. Okay. So I can make x minus j as just basically their respective starred one. So I can just put in place of this, which means ui of Tj comma x minus j star less than equal to x hat j x minus j star. Okay. So I should come back here now, the definition of weakly dominated. Okay. So here actually there is a small error here in this definition. So the weakly dominated was that I said that this inequality could be, you could have equality in one, right? Then it's when we say you could have equality, and so but it has to be strict for at least one. A strategy cannot weakly dominate itself. Okay, you cannot have equality for all. Okay. So if the inequality above is weak but holds with strict inequality for at least one x minus I, then xi is said to be weakly dominated. Okay. So that means you have this here is replaced with a less than equal to, but there should be at least one case where there is a strict. Okay. The reason for the including this is basically you avoid degeneracy where you have equality throughout, because then you can effectively start repeating strategies one after, just copy pasting and repeating strategies, and that then they will all end up dominating weakly dominating each other, and that creates a whole bunch of degeneracies. No, we will see that one second. Alright, so xj is weakly dominated, that means there exists a tj like this. So tell me, this tj is weakly dominating xj. Now is tj present in s hat j or not? Why is it present in s hat j? Yeah. Okay. This is where I needed it. Okay. So if tj could be equal to x hat j, then it would be a degenerate case where it is not it is dominating itself, weakly dominating itself. Right. So, but that's of course that's a different thing. So this essentially weakly dominated means that essentially it is not actually equal to, this actually implies that tj is present, is distinct from x hat j, and hence tj is in s hat j. Now if tj is in s hat j, what does this mean? If tj is in s hat j, then I have this term here. This is for all xi in s hat I, right, and for all I. So in particular, I can take xj here as tj because tj is present in s hat j, right. So therefore, I putting xj equal to tj gives me ui of x star is less than equal to, sorry, uj of x star is less than equal to uj of j comma x minus j star, and tj comma x minus j star is in turn less than equal to j. That in turn is less than equal to uj comma x hat j comma x minus j star. So, in other words, we have shown we got this for free Sj minus x hat j, and for x hat j also now we have shown the inequality. So, in other words, x star is a Nash equilibrium. All of this basically, from here we conclude that this is a Nash equilibrium. No. Strict inequality was for at least one of the other strategies. See, for at least one x minus I, this should be strict. That means at least one profile of strategies that the others would play, xi dash should be better than, strictly better than xi, right. So, Tj is the strategy which is the dominating one, and dominated is x hat. Okay. So, from here then we can conclude that is a Nash equilibrium of G. What this is saying is that once you, again repeating, that if you eliminate weakly dominated strategies, you cannot create new equilibria. You could eliminate equilibria, but you cannot create. Yeah. Yeah. So, it is just to avoid this degeneracy that a strategy cannot weakly dominate itself. Otherwise, you can end up with a lot of vacuous statements, I mean, what does it mean to eliminate a weakly dominated strategy? Every strategy will weakly dominate itself, and you will keep eliminating every strategy, right?
But then again, I can have two strategies that are completely equivalent.
Yeah.
With respect to the utility function.
You can eliminate one of them. You can eliminate one of them if as a weakly dominated one.
But then I will have to use this definition.
Sorry, what?
So, if we use this definition, strategies are completely equivalent with respect to the utility function. I cannot run this argument.
Yeah, you cannot. If there are two are equivalent. Yeah. So, that is actually a case, more of a case of, okay, yeah, I understand what you are saying. So, if you have two strategies that essentially are identical, right, it's just you can say, that's I think more of a case of poor problem formulation. Actually, you have just unnecessarily created another strategy when there is, concretely there is no, they aren't different strategies.
But my strategy should be that I have to fix to all of it, right?
No, but regardless, so the point is, so regardless of what the other is playing, these two strategies are identical for you, right? They are identical for every case. That's what. So then you cannot eliminate. No, then that's all the more reason why you cannot. No. This is for a player I. For the other players, if they are not identical, that is all the more reason why you should not be eliminated. Because you are changing the strategic considerations for the other player then. So, you are basically saying that regardless of what the other player does, I don't care, but that does not mean that they can be eliminated. You can drop one of them. The other guys care, I mean, so. Yes. So, that means I can drop one of these, if there is one that is strictly better for me, if I have a, if there is a third strategy that weakly dominates these two, I can eliminate these two and stick to the dominating one. But yes, if then you can, in that case you cannot eliminate them. I think I have an example. So this example, I mean, I don't know if it is actually a true story, but it has been referred to in multiple settings. I think it's appeared in some movies and all that as well. So there are two paths. This is called the example of the Battle of the Bismarck Sea. Okay. So there are two generals here. One is this is the war between America and Japan. So there are two generals who have to make decisions about which direction in which about the direction in which they will be sending their troops. Okay, the generals are Kenny and Imamura, and I'll tell you the story. So General Imamura has been ordered to send transport troops across this sea, and General Kenny has been ordered to bomb the troops. All right, that is the situation. Now Imamura has two choices. Okay, there is he can go north or he can go south. The north route is shorter, the south route is longer, and Kenny has to decide where to send his planes. Okay. Now, if Kenny sends planes to the wrong route, he can recall them, but the number of days of bombing is reduced. Okay, that is the situation. So the payoff matrix that you get is you can write it like this, that okay, so this is, so if Kenny goes along the north route is the shorter one. So both players are looking for the maximum. So so there is nothing that, so Kenny doesn't have doesn't have any dominated or dominant strategy, because here 2 is greater than, you have 2 greater than 1 and 2 less than 3. Okay, so there's nothing that Kenny can eliminate, but Imamura can eliminate. So he is also looking for the largest value. So now -2 is equal to -2 and -1 is greater than -3. Okay. So north is better than south for Imamura. Okay. Now remember, but north weakly dominates south, not strictly. Okay. Now so Kenny can reason in this way that, well, Imamura I know is rational, so he will not go south, he will instead go north, and when he is going north, what should I be doing? I should also be going north. Okay. So what's happened is that this is not exactly the thing that you guys were talking about. It's not the completely degenerate type of case. But you see, what has happened is Imamura has ended up eliminating a weakly dominated strategy, and in the process, effectively, and knowing that, then Kenny knows that north is weakly dominated. If Imamura eliminates that, then from that logic, I can also eliminate south and bomb him in the north. Okay. So effectively, what has happened here, so if you reason about it in this way, essentially the fact that north and south are indifferent for Imamura, right, has gotten basically completely eliminated because he has chosen to eliminate weakly dominated strategies. Okay. So if you can try, when we go to mixed strategies and so on, we will see that there is a better way of solving this particular game than doing this. This is tactically not the right way to approach this. And the fallacy is exactly in this, that you are eliminating something that is weakly dominated. And so I have not got to that yet. So when you eliminate something that is weakly dominated, forget what you are talking about is an even more degenerate case, where there are two strategies that are same, identical, okay, in terms of payoff. But even when you eliminate something that is weakly dominated, right, it is you end up there is a chance that you will end up eliminating equilibria. And you end up eliminating equilibria means what? There are possible strategic outcomes that you are basically letting go of. No. See, that is not a good enough justification. That's the point. So, see, so we cannot. So, what I have not completed my story yet. But basically, weakly dominated strategies will, in general, lead to loss of equilibrium. Strictly dominated do not lead to loss of equilibrium. So, strictly you can freely eliminate. Weakly you can eliminate at the risk of losing equilibrium. So, at the risk of no, but loss of equilibrium means that it's a strategic outcome that could have been possible, which you have now let go of, right?
If we are assuming that we can eliminate both and we get a national equilibrium, there could again be a national equilibrium.
It is a Nash equilibrium, but there could have been another Nash equilibrium that would have been better. No, but that is all, that is provided all you are looking for is this particular property, right? I mean, there is more to it than just that. See, the point is, see, weakly dominated strategy, the elimination of weakly dominated strategy has perils with it, and that's the point I will be making, I'll be making soon. Okay.